So good afternoon or good morning from myself, Michele Merelli, and I'm here today to discuss about the new feature of Particleworks, this meshless simulation tool for computational fluid dynamics. We are collaborating with PowerSys in promoting meshless simulation all around Europe and also outside of it. So here you see my references, so please feel free to contact me for any question related to this topic. So briefly introducing the methodology for those of you that are not aware of it. So just know that Particleworks is a meshless CFD tool for computational fluid dynamics, and there are some differences between Particleworks and other software like ANSYS Fluent or StarCCM. And the main difference is that here we don't need to generate a mesh, and we don't have to prepare the CAD for the simulation. Actually, we can use the CAD as it is with the solids as designed by design engineers in our company. So really, this speed up significantly the simulation workflow because we don't have to simplify the geometry, we don't have to mesh the fluid domain. Everything is handled automatically by the software. Moreover, the method, moving particle simulation, is intrinsically very parallelizable. And because of that, we can run on GPUs, graphic cards, that are more and more let's say, potent and fast every day that passes. So we can really join the GPU revolution that we are seeing all around with NVIDIA presenting graphic cards with crazy numbers in terms of simulation times every few years. So because of all of that, we're looking into a method for simulation that is more generalized, more democratic, and faster, and doesn't require, let's say, 100 or 1,000 of CPU core, big cluster. And in general, as you can see here, the workflow with moving particle simulation as compared to meshed-based CFD is faster. Usually, we move from 1 week to 1 day of workflow for specific cases, for specific type of flow, like this one that we see here. Particleworks is widely applied in the automotive sector for splashing or oil jets in e-motor, cooling the e-motor, bearings lubrication with grease, soiling or wading in the automotive sector, like you see here, but also engine and piston cooling type of application. So as you can see in all of these cases, we have multi-phase flow with jets, splash, and this kind of phenomenology of fluid flow is very difficult to capture with mesh-based CFD, jets. So whenever you see this kind of flow, you know that moving particle simulation can be very beneficial. So the agenda of today's meeting is actually to go a little bit in depth about the method and the new features, assuming a bit of experience on the software, but it will also be a good way to give you examples of application, real life application of the software and validation as well. So we will see the key feature introduced in the latest release, but then also I will discuss about how we can model thermal aspects of our, let's say, digital prototype with Particleworks, but also airflow analysis and some more advanced topics. So one of the most important features of the latest release is the possibility to have a multi-resolution region. So basically, you can see here that the fluid is discretized by particles. At the beginning, it's only discretized there, but whenever it enters this box, the particle size, so the mesh, dynamic mesh on which we compute Navier-Stokes equation, is actually reduced. So this is very advantageous because it let us define regions where the particle can be reduced to capture better flow in small gaps without having to, let's say, use this small particle size everywhere in the domain. So very convenient type of approach. So this high resolution region can be a box, but also a file, so a volume, like an STL volume. I see there are questions already. Feel free to ask them in the chat, and we will address them at the end of the presentation. So thank you. So an example of multi-resolution is shown here for weighting application. So the idea is that you have to discretize, in this case, quite a bit of a volume. But in some cases, you might be interested in flow in small gaps, like at the radiator side, to evaluate water intake. So of course, one strategy could be to use a uniform 5 mm particle size everywhere in the domain, but this is not ideal because, again, we are looking at significant longer simulation times. One strategy could then be to apply a multi-resolution region close to the entrance there, and as you can see, we have a combination of the two particle size with basically a reduction of the computational time from 8 hours to 3 hours, just by using this kind of strategy. So in some cases, it's very advantageous and can speed up the simulation while answering all the engineering questions. And here we have another example of soiling. So we have a track with cars on top, and we can see the light particles close to the track. Those are particles with a multi-resolution type of feature and smaller dimensionality, and we can see the wetted areas on the cars due to those small particles. Okay, so soiling is one example, but in some other cases like e-motor cooling, it's also important. So we see increasingly oil cooling in e-motors, because this strategy with jets coming also from the shaft showed better cooling efficiency as compared to a water jacket around the stator. But one tricky part could be small gaps in the rotor channel, distributing channel, like you see here. We have a small gap of 0.25 millimeter, and if we were to use a 0.3 millimeter, you can see that the gap is not captured. On the left side, we have 0.1 millimeter, and we see the gap that is captured. And in the middle, we see the multi-resolution approach with a, let's say, box just placed on top of the small gap. And basically, we are able to capture the flow here without compromising simulation times everywhere in the domain. And also in this case, so you see that 0.3 millimeter for this jet is the same as this one. So we don't need to maybe discretize 0.1 everywhere, but at the same time, we capture the flow and we have similar pattern in the flow there. So very strong approach to speed up simulation. Other features and let's say new aspects of Particleworks version 8 is the possibility to model highly viscous fluids. Okay, so in this example, we have an image showing chocolate simulation. So there is now a dedicated solver that is slightly different than moving particle simulation. There are some small numerical differences in the background, but basically this new solver lets you compute for grease, chocolate, cement, concrete, let's say, very complex and highly viscous or non-Newtonian fluids. with good results. So we can have different type of modeling. We can implement different type of laws for non-Newtonian fluids, either predefined or custom made, like also with tables or functions that the user defines. And in this direction, there is also snow modeling now, advanced snow model inside Particleworks, and it's known as more Coulomb Bingham fluid. So basically, the idea is that now we can, let's say, describe different type of wettability, let's say, percentage of the snow with different behaviors depending on the, let's say, the parameter of this more Coulomb model. Okay, so it's very convenient whenever you are interested in snow modeling for different application. Now you have an advanced method integrated very, very efficiently. So as I mentioned, Particleworks runs on GPU, so graphic cards, and it scales quite well also with multi-GPU. Here we have a graph showing how the scaling can be performed and how the solver scales basically linearly when you increase the number of GPUs. So as compared to 48 CPU cores, you can see that one GPU can be actually approximately 10 times faster. So basically one A100, NVIDIA A100, can be compared to 480 cores. Moreover, if we start to use multi-GPU capabilities, we can see that we go actually 3 or 4 times faster than just one GPU. So really, we can see that with also compact hardware, because one GPU, gaming, especially GPU, can be integrated in a simple workstation. So with only that hardware, we can have a good, let's say, simulation time. Let's discuss thermal capabilities of the solver, because this is very interesting, and I will give you some examples. So Particleworks doesn't just integrate, let's say, fluid analysis. So it's not only a CFD software, but it also includes some equation for heat transfer in the solids or air, let's say, so an air solver based on finite volume method, and maybe I will also come back to that. But with respect to thermal solver in solid, you can see here the different approaches our simulation could take. So we can analyze, let's say, fluid or solid temperature variations depending on the degree of complexity of the thermal simulation we want to set up. But let's say most of the time what we do is to run first a CFD simulation inside Particleworks that is able to give us ideas of the HTC from, for instance, nacelle correlations due to oil or air. And then from that, we can map the HTC on the, let's say, key elements of our model. Like in the e-motor case, we could map the transfer coefficient on the windings. And we can transfer those maps as CSV files to a solid heat conduction model that is basically the same model used for the CFD simulation with just a couple of variation of the numerics. So effectively, we use the same model both for fluid simulation, but then also to estimate temperature in the solid while considering the heat transfer boundary condition and also possible heat losses, okay? So let me give you an example here. We have on the left the map due to heat transfer coefficient of oil on the end windings of this e-motor. And basically, we can transfer with the CSV boundary condition this HTC, so cooling of oil, to the thermal model of Particleworks to predict temperatures in the windings. So again, we see one digital model, meshless, that really speeds up the workflow for temperature prediction, because at the end, of course, especially in the e-motor domain, we want to predict hotspot very, very fast, okay? So just to present now a little bit of results and validation of the method with respect to the thermal but also fluid flow, I want to showcase let's say some presentations that were held in our conference last June in Bergamo, close to Milan, Italy. We had several presentations from Polestar, Ducati, Gamma Meccanica, Carraro, Chalmers University, Rimac, PowerTech, SKF, Punch Torino, Tremec, and GIMA on different topics like transmission, lubrication, e-motor cooling, piston cooling, and many more. So let's start with piston cooling. There is this presentation where basically the workflow, as I discussed with Particleworks, integrated both the fluid and the solid via the CHT model, can represent a new computational aided engineering methodology for effectively run every aspect of our model in one workflow, in one workspace. So the idea was here to understand how well the method could compare to previously held workflow, the existing methodology, and also actually to finely tune, in this case, the piston cooling type of correlation to predict HTC. So I don't want to go too much in depth here, but basically what was done was to script and adjust precisely for this application the Nusselt correlation for heat transfer coefficient, integrating, let's say, experimental results. So of course, in this kind of impinging jet type of flow, there are several regions depending on how distance we are from the impinging jet region. So you need to tune a bit the Nusselt correlation describing the heat transfer coefficient due to that jet, and it was done correctly with the possibility to script the HTC correlation. And this was also then applied, this HTC map, to the thermal solver in order to compare the predicted temperature in the piston cooling application as compared to some literature results. Here you see the jets of oil going through the piston and cooling the gallery of the piston. So together with HTC prediction, of course, this tool is very suitable to understand the flow pattern and possibly some undesired, let's say, interactions. Another example of application of the software for temperature prediction is for this example. So we are looking at a clutch or a brake system. You basically have oil injected in the shaft and then flowing through the disc. There are several discs here. And as you can see, there is a small film of oil forming through the disc. And at the end, you want to understand the flow pattern distribution between the different discs and also the most critical areas or less wetted areas in the disc. And at the end, of course, you want to apply the cooling of oil to the thermal model. So basically what was done was to first run the CFD simulation as mentioned, and to then map, you see here in light blue, the heat transfer coefficient due to oil on the critical and wetted areas, and then we could apply power sources in the disk area, and at the end, basically predict temperature. So here is the full workflow. On the left, you see the oil flow in light yellow, with particles going through also the small gaps between the jets, between the disks, sorry. And here you see an overview of one disk with flow pattern and most wetted areas or most cooled areas in red. And on the right, we have the model, the temperature prediction by the steady-state thermal model, integrating the boundary condition I mentioned in the previous slide. So both the heat transfer coefficient due to oil and the heat sources. So very interesting, because you can see an imbalance of heat in the disk area due to different flow distribution, because you see maybe a little bit here, not all the channels are interested by the flow in the same way. Okay, so because of that imbalance due to rotation and so on, we could not, at the beginning at least of the design, provide distributed flow all around the disks. Another example of the application of the thermal solver, in this case with experimental validation with thermocouples, is the presentation from Carraro, this company working on transmission and reducer for instance, the agriculture sector. So the idea here was first to, of course, use the software to validate oil flow and visualize the oil flow splashed all around in this system. But at the end, the method was, let's say, integrated also with the thermal solver. So Carraro uses the software now for more than 3 years, but they wanted to investigate and develop a model also for temperature prediction. And at the end, they wanted to compare with previous ANSYS mechanical results, but also, let's say, validate the temperature prediction with thermocouples, as mentioned. So what we are looking at here are 4 different configurations, so 2 different rotational speeds and rotational directions. So first thing first, you want to see the flow. So of course, the first output of the simulation is usually to visualize the flow, to understand the churning losses, or understand if the bearings are well lubricated, for instance. Okay, so compare this kind of configuration. So the standard output are those one. You could also maybe just change a baffle, change some geometrics of the system very easily, and understand how that impacts the flow. But at the end, what you want to do is to map the transfer coefficient. As you can see here, we have the maps for the 4 different cases. And later on, those maps were applied with the same workflow I discussed for temperature prediction. So the model integrated localized mechanical losses at the bearings. Those were estimated from internal know-how and ISO indication. So let's say standard type of indication from ISO. Then the model was applied with the HTC maps that we saw here. And those are the temperature resulting from the steady-state thermal model inside Particleworks. You see that at the bearing side, we have higher temperature. At the top, we have higher temperature because we have less oil, okay? And when we increase the velocity and the speed of the rotation, we have higher temperature as well. But then the question was how those temperatures compare to thermocouples experimentally placed and validated. So you see here the experimental setup. We have at the 6 bearing side thermocouples, and on the left we have the difference between the temperature prediction and the simulation results. The temperature, sorry, the experimental temperature and the simulation results. We do see that for all the configuration, we are in a range of less than 10 degrees for the different thermocouples, and we have quite good agreement with the results. This was basically the first model we built, so not a lot of tuning going on. And yeah, the results showed promising, a promising start for further improving the simulation workflow in Carraro. As mentioned, Particleworks is widely applied also in electric machine and e-motors. So here we have the presentation from Chalmers University. They are investigating, for instance, different oil cooling strategies. So the idea here is to have an e-motor cooled by a pre-initialized oil inside the e-motor itself. So due to the rotation of the rotor, this oil amount will be splashed around on the windings and on the coils to cool them. Of course, there is a trade-off between the amount of oil we inject in the system and the losses due to the oil itself, let's say the resistive losses due to the oil on the rotor. Okay, so what was done here was to test for different RPM and different oil amount, as you can see here, very quickly the configurations. We see that the mechanical losses, this is an output automatically generated by the software, mechanical losses increase quite significantly when we increase the amount of oil in the system and when also we increase the rotational speeds. So you can see that it's not a linear increase. So even if, of course, at 1 liter we can have better cooling, this basically represents, let's say, twofold, if not more, increase in the mechanical losses. But as you can see here, we have also the windings temperature prediction. Also in this case, the method was validated experimentally, both with a clear casing to understand the flow pattern inside the e-motor, but also for the temperature prediction that resulted in at the winding. So we see here 3 sensors on the windings, and when we apply the heat transfer coefficient maps from Particleworks to the thermal model, we see that at increasing loads, increasing rotor current, we have good agreement between the experimental and the sensor signal. So also this method for e-motor was validated. I will be happy to further discuss this example in the question. Now I will just move on with some other small features. So for user of Particleworks, this is very interesting because what we had with the new version was the ability to apply now a volume, not only a box, but a predefined volume like this bottle for the air or the water simulation. So basically, we can define a custom shape for our simulation domain. You can see here, those are air finite volume cells initialized by the air solver that is integrated in Particleworks. We have here another example of that air solver for a piston cooling type of application. Basically, as mentioned, inside Particleworks, we have not only fluid, so moving particle, solver for jets or splashing, but we also have this dynamic finite volume method. That is what you see here in the piston cooling application. So basically, we can couple the air simulation with the oil simulation, for instance, very efficiently. And here is another example of the solver
for air integrated in Particleworks. In this case, it's applied on the external aerodynamics of a track. And actually, as you can see here, there is a grid, a dynamic grid all around the walls. So effectively here we are looking at a Lattice Boltzmann type of solver for transient airflow, and all of it is coupled and integrated in the same solver, and everything is meshless as well. So very complete, and let's say there are several solvers integrated in the same license here, so you might want to understand more about it, of course, with question and further discussion with us. So coming a little bit towards the end of the webinar, I just want to present another tool that is called Simunima, and this one basically lets you move from the simulation results to eye and rendering of the results for, let's say, a VR type of application, or also to integrate those elements in a let's say better looking video. So this is the workflow. Basically, Simunima converts the simulation results to a format that is suitable for 3D computer graphic tool like Blender or Unity for at the end generating an output like a video, eye rendering video, or a VR model. Here we have an example of a VR model that was built with this workflow. You can see the e-motor cooling type of application. By the way, if you scan the code, you will be able to access it also with your phone. And so in this way, we can basically generate a VR model from Particleworks results in order to better show the results to our customer and to have a better visualization of the flow. Okay, so you see the accumulation, the oil jets coming from the center, and the accumulation between the windings and also on the housing. Okay, so I don't know if you were able to launch this model on the browser, but it's very nice, I think. So have a look at that, because you can really see the full model with a nice resolution of the results. So with that, I really hope that you enjoyed this presentation, and I'm more than happy now to address the questions and further discussion with you. So here, by the way, we see the let's say flow in the system I mentioned beforehand with the high resolution rendering tool. Thank you for your time for now. So let's see at the question, as if. So the first question is, what is the difference between smooth particle hydrodynamics like Preon Lab? So they are both particle-based method. Moving particle simulation is for incompressible fluid, while SPH is for compressible fluid. And I can tell that as compared to SPH, the stability conditions for moving particle simulation are actually less demanding. So we are looking at usually faster simulation times. So in terms of comparing CPU and GPU, I hope I answered that question in the slide I showed. So with just one GPU, you are looking at performances in the range of 500 CPU cores. When you start to have multi-GPU computation, you can scale quite linearly, depending on, of course, the hardware, the number of particles in your system, the complexity of your system. And the other question is about finite volume method. So how FVN can be meshless when coupled with Particleworks. So it's a meshless, basically meaning that we don't have to generate, we don't have to think about the mesh generation, because as you can see here, at the beginning of the simulation, there is a Cartesian grid automatically computed and handled by the software. So it's meshless in that regard, okay? But it's a finite volume method, and it's coupled intrinsically with the Particleworks, either in a one-way or two-way fashion. So we can have a fluid influenced by the air, or actually also air influenced by the fluid flow. So different options there for air simulation. And again, if interested, we can go further with private meeting. So please feel free to ask more questions if you like. In the meantime, I would suggest you to go over particleworkseurope.com. You find basically in the experience part, you find that all the public material, and you can have more info about the method and the features. And again, just drop me an email with your question, or if you want to also possibly test the software. We have several introductory days on a monthly basis, so you can easily get in touch with us. Can outputs in VTK format? I don't know about VTK format. Sorry, Azif. Can you articulate a bit more? Yeah, for ParaView, I guess. Yeah, I mean, every Particleworks basically lets you export in CSV files that can be then integrated in any type of let's say post-processing tool. Okay, so for sure you can then import in ParaView. Yeah. Okay. So if there are no other questions, I want to thank you all for your kind interest on the software and in these new features. Again, I hope we can continue our discussion, and possibly, if you are not familiar with the software, we can open up some trial for you. And again, I want to thank also our partner PowerSys for hosting and help us in hosting this webinar. So thank you all again for your time and interest, and feel free to drop me an email anytime soon. Bye, everyone.